Hey everyone, welcome to lesson 11.1.2, volumes of similar solids. In this lesson we are kind of reviewing a topic we've already seen before. In this case, similarity. So except this time we're going to be focusing on volumes. We have talked about similarity with similar shapes, how that affects area. So we'll be reviewing a little bit of that today as well. We are going to need to know a little bit about the difference between area and volume, and so let's kind of discuss the differences there. Area is the number of square units, right? The actual squares, physical squares that fit inside of a two-dimensional shape or space. Volume is the number of cube units. So that's really the main difference is, are we counting squares or are we counting cubes? And so cubes are three-dimensional and squares are two-dimensional. So even if I have like some odd shape, if I draw this, I'm going to count how many squares actually fit inside of this shape. So that would count me the area of this weird shape. If I want to find the volume of a shape, then that pretty much means I probably have some larger three-dimensional shape, and I want to see how many maybe cubes fit inside of that shape. And so that one might be made up of a bunch of cubes. All right, so that's kind of the main difference between area and volume. Make sure you know the difference. We've already talked about how to find the volume of, I think, prisms and cylinders at this point. And we're going to be talking about a couple more shapes in the next lesson. But before that, we just want to see, is there a way we could actually find the volume of a shape without having to do all the calculations? And so the nice part is there is, as long as we have a similar shape. And so, like I've said, we've seen this before with when we focus mainly on area. So all of this part before that I'm highlighting here, we've technically seen and dealt with. The only thing new we're adding is the volume portion of it. So if I give you the linear ratio, so if a shape grows by a certain linear ratio or scale factor, or sometimes we'll say zoom factor, right? All those terms are synonymous with each other. So here we have the linear ratio. Let's call it R for ratio. And so if I know the linear ratio is R, what I also know is the perimeter ratio, which we've talked about before as well, is also going to be R as well, because perimeter is made up of all the sides, the side lengths, and linear ratio really is the ratio of the side length. So linear ratio and perimeter ratio are focused on how long the side measurements are. When we talk about area ratio, then we actually have to multiply to get the area, right? We have two dimensions. So base times height or length times width, and we're going to be multiplying. Well, when we multiply, we end up with a ratio that is squared. So the nice part here is, if you know the linear ratio or perimeter ratio, then instantly you know that the area ratio is going to be the same number except squared. And like I said, the new part that we're going to be talking about today is volume ratio. And so that means if I cube that ratio, it will tell me what the ratio is of the two volumes. Again, when we talk about ratios, that assumes we have two shapes, similar shapes. So two prisms, two cylinders that we're comparing or we're using together. So if for some reason, let's say the linear ratio is given to us, and I say, oh, linear ratio is 2. Well, then that means the perimeter ratio is 2. which really just means the sides are going to be twice as big. That's what that means. But if the sides are twice as big, does that mean the area is twice as big? Well, no, that means we're going to take that 2 and we're going to square it, which means the area is actually 4 times as big. So sides were 2 times and area was 4 times as big. So now the new thing is, what is the ratio going to look like for volumes? So how many cubes would actually fit in a 3-dimensional shape? So the nice part is we use that same 2 as a linear ratio, and we're going to cube it, and this is going to give us an 8. All right. So, and these would also, these could be written as 2 over 1, 2 over 1, 4 over 1, 4 over 1, and 8 over, keep doing it, 8 over 1. So don't forget these ratios technically could be written as fractions in case you forgot that. All right, and let's do 2 more of these actually. So I'm going to do, let's say, 3. So that means we're going to have a perimeter ratio of 3, and we're going to 3 squared is going to give us 9. And so the question for you is, what do you think the volume ratio is going to be? Final answer. Let me know what you think that is. All right, let's see if you got this correct. We would do 3 cubed, which would come out to, I think if I do this correctly, 27. All right, so I'm going to do one more. Let's see if I could squeeze in one more in here. So I'm going to do a fraction this time. So let's do, what if I do, instead of a whole number, what if I do 1/4? So if the linear ratio is 1/4, that means the perimeter ratio is going to be the same. Area ratio, we're going to take 1/4 and we're going to square it, which is going to give us 1 over 16. And let's see if you could tell me what the volume ratio is for a shape with a linear ratio of 1/4. All right, let's see if you got this. So I would do 1/4 cubed, and so this would end up being 1 over, right? 1 cubed is 1, and 4 cubed, I believe this gives us, is it 64? Right? 4 times 4 is 16, and 16 times 4 gives us 64. All right. So now we have an idea of how to calculate these ratios. Let's see why we need to know these ratios. And why is it that these numbers are like this? So here's an example drawn out for us. I have 2 prisms that are similar. And so I've written out the dimensions of the first one, where we have a height of 1, there's a width of 2. The base is going to be a 2 by 1, right? So 2 by 1 on the bottom, or you could say 2 by 1 on the top as well. And I noticed that the dimensions, you'll notice the dimensions of these go from 2 to 4, and this goes from 1 to 2, and this goes from 1 to 2. So you'll notice all the measurements double in size. So as soon as I see that, as soon as I see all the measurements double in size, that tells me something. That tells me that the linear scale factor, right? Linear scale factor in this case is going to be, 2, right? Or let's say 2 over 1. Okay, so we could very easily count the number of cubes in the first picture. So even if we didn't know how to calculate volume, you should know how to count. So I notice there's 2 cubes. So that means this has a volume of 2 units cubed. All right, so in the larger prism, we could probably count them the same, but the larger this shape gets, it might be a little bit harder for us to count. So if only there was a faster way of doing that. And so the faster way is really by us using the linear scale factor, which we just figured out. So if I know all the sides are twice as big, then the question is, how many more cubes is there going to be? Now, if I remember correctly, we actually did this up on top. If its linear scale factor is 2, the volume, because cubes is volume, is supposed to be 8 times as many. So what that means is if we take 8, in this case I'm going to take 8. Oh, let me explain why. So volume scale factor means this is going to be 2 over 1 cubed, which is 8, or 8 over 1. So that means I could do 8 times this original 2. Let me redraw that. So this is 2. And so that means our volume is going to be 16 units cubed. All right, so that's kind of an easy example. If we count the number of cubes, you might notice that we could actually count the ones on top. 1, 2, 3, 4, 5, 6, 7, 8. So that means this top row has 8 cubes, and right underneath it, right, the row below it should have another 8, which means it's a total of 16. So you'll notice we could have easily counted, but in a more complicated or larger, like if there is 1,000 cubes, we're not going to sit here and count 1,000 cubes. And so it would be a lot easier for us just to multiply the volume scale factor times the number of original cubes. All right, that's definitely a lot simpler. All right, so we're going to look at a couple of other examples, and then I'm going to use, I think I'm going to remind you of proportions that we've used before to find missing area. All right. So let's look at this example. Now, even though it's nice to have a picture or visuals, the reality is when we're using similar shapes, it doesn't really matter what the shape looks like or even what the shape is. So you'll notice in this problem it says an object. That object could really be anything you want, right? I could have said, oh, the car increases its dimensions, or the book, right? It really doesn't really matter what the object is, but it increases, so that means it's getting bigger. Its dimensions means really it's another word for side lengths, right? That's just a fancy word for saying side lengths, by 300%. So that doesn't mean it's 300 times bigger. That means it's growing 3 times bigger. So that's something we're going to write down. And then it had an initial volume of 4 units cubed. So now we know what it started with. We want to know what the new volume is. All right, so if it helps, you could always draw a picture or some random shape if it helps you to visualize it. In this case, we're told the linear ratio, right, dimensions are the side lengths, are going to grow by 300%. So that's them telling us the linear ratio is, so this 300, so this is 300%. This could be written as a fraction, which is 3 over 1. All right. Now, from that, we need to figure out what the volume ratio is. All right. So we'll use what we've learned before, and we're going to take this 3 over 1, and we're going to cube it. right? Since we're talking about volume, it's cubed. If we want to know the area ratio, we would square it. And so this is going to give us 27 over 1. Right? So this is our volume ratio. Right? So now what we want to figure out is the actual volume. Right? So this is what I'm going to remind you of an approach we used before, and that is using proportions, which means two fractions equal to each other. So in this case, one of those fractions we already know. So I like to put that one here second. So this is going to be 27 over 1. So now what I know is this 27 over 1 represents the ratio of the two volumes. So that means I need to put the two volumes on this first fraction. So only one of those volumes was given to us, the initial volume. So the question is, am I going to put a 4? Am I going to put a 4 on top, or am I going to put a 4 on the bottom? Well, think about it. If it's increasing in size, it's getting bigger. Think about these two numbers. Which one's the larger number? Right, 27 or 1. So if 27 is the larger, then that means this is where the new volume is going to go, which means the only option left is for 4 to go on the bottom. All right, so our new volume, I'll put X just to represent the missing volume, and then we could solve this. So cross multiply, you'll end up with X equals to 4 times 27, and then once we multiply those, 4 times 27, what does that give us? I can calculate that one. Let's see, 4 times 27, 108. We are talking about units, so make sure you have the correct units there. So this would be 108 units cubed. All right, so that would be an example of how you do this problem. Notice there is no picture, so we can't just count cubes. We need a strategy where we could actually just use some algebra skills. And so if you basically were taking a fraction, changing it to a new fraction, and we're going to set that fraction equal to a ratio, where one of them is going to be x. So we just have to figure out where to put the volume and then solve. All right, so that's kind of the general idea of what you need to be able to do. We're going to practice. I think this is, we have two more problems to do. Here we have two cylinders, poorly drawn cylinders. And so this is taken from a problem that's asking us if we have, let's say, this container, cylinder container, and the standard size holds 12,000 gallons. And it happens to have a diameter of 4 meters. So that's this first shape. So the diameter is 4 meters. And if we increase the diameter to 5 meters, it creates this new cylinder shape, which we call the jumbo shape. And the question is, how many gallons does it hold? So is it beneficial for us to switch to use standard cylinder or the jumbo cylinder? What's going to hold? Well, one of them is going to obviously hold more, let's say, gallons of oil, but when we start to look at cost of maybe these containers, we have to decide, is it worth it or not? And so first we need to figure out how many gallons does the jumbo container hold. All right, so first we need a linear ratio. Well, in this situation, the only linear measurements we have are the diameters that were given to us. So that's considered a linear measurement. So now we just need to make a fraction. So we have a 5 and we have a 4. So let's use that. I'm gonna put 5 over 4. All right, and so now that we have a linear ratio, we could easily create our volume ratio. Let's see if you could tell me what the volume ratio is going to be for this problem. All right, let's see if you got this. So 5 over 4 cubed. All right, so that means you'd have to take 5 cubed. 5 times 5 is 25 times 5. That's 125 over, then we would do 4 cubed. 4 times 4 times 4, I believe, is 64. All right, so there's our volume ratio. If we want to figure out the volume of the jumbo, again, we could create our proportions. So I would start with, I like just to draw the fraction bars and the equal sign. I'm going to copy this fraction 125 over 64. And now I just need to figure out, I have the number of gallons for the small one, right? Standard is the smaller shape. So it looks 64 is a small number here. So I'm going to put 12,000 gallons on the bottom, which means I need to figure out what X is on top. And that'll give me the volume of the jumbo. All right. So let's see if you could calculate this. I'm going to give you a few seconds to try to calculate this. Final answer, let's see if you could tell me what X is equal to, or volume of the jumbo. Don't forget your units. These are going to be gallons. In this case, because gallons is a volume metric, you don't have to put, it's not gallons cubed, you just have to put gallons. All right, so make sure when you write out your answer. All right, so hopefully you've cross multiplied and got a final answer for this. Let's see. So this is going to be 64x is equal to 125 times 12,000. All right, and then we're going to, if I divide both sides by 64, I should end up with 12,000 over 64. So that's the numbers you need to multiply and divide. And so hopefully, if I did this correctly, this is going to come out to, see if you got this correct. This is 23,437.5 gallons. All right, so there's our answer, 23,437.5 gallons. Or gallons. All right, so that's how much the jumbo container holds, which is close to double the size. You'll notice 1 meter wider, and all of a sudden that jumbo container holds almost double the amount of oil. All right, so something to think about. All right, and then this next one, I wanted to do a problem where the shape was actually reducing in size. And so I've kind of started this for us. In this case, we have a volume of a pyramid, which you may or may not know about at this point. We do go over pyramids in the next lesson. But like I said before, it doesn't really matter what the object is. All that matters is the information they're giving us. So in this case, they told us the initial volume of this pyramid is 138 inches cubed. I want to know what the volume is of a pyramid with dimensions half the size. So the new shape, right, the new pyramid is actually going to get smaller. Right, so it says dimensions, again, that's telling us the side lengths. half the size. So right away they've told us the linear ratio is going to be 1/2. All right, so this shape is going to get smaller. All right, so let's then, using that information, we would calculate the volume ratio. So in this case, instead of 1/2, we would be using 1/8. And so we could set up our proportion here. And so I'm going to put two fractions equal to each other. Again, we'll use the 1/8. All right, that's going to be the 1/8. All right, so I'm just taking that number here. So now, how do I set up the first fraction? Well, let's think about this. They've given us the volume of the original, which is, in this case, is going to be larger, right? So the original one's actually going to be larger. And so the larger one number, I notice, is 8. So this is going to be 138. So we're trying to figure out this measurement. All right, so let's cross multiply this. So this is going to be 8x equals to 138, which then we'll divide both sides by 8. And so if you do 138 divided by 8, this is going to give us 17.25. And I think these were inches cubed. Yeah. All right, so new volume, right? New volume is equal to 17.25 inches cubed. All right, so that's the general idea of what you should be able to do. You'll notice the work is very similar on all these. Take your linear ratio, convert it to a volume ratio, and then set up a fractions you could cross multiply and solve. All right, so that's a simple version of it. Hopefully you don't have too many questions, but if you do, let me know, and I'll try my best to help you out. All right, thank you.